Hello and welcome to my YouTube channel. In this session we will see the design of continuous one-way slab. This is the topic from the RCC structures. So in this we will see the design aspects, and we will also see the codal provisions. This design of continuous one-way slab is divided into two parts. I have created two parts. There is part 1 and part 2. So the second part, for the second part, the link of the second part is already provided in the description box. Also, I will show the codal provisions and the criterias for the this calculations. So let us move ahead. So this will be the flow of design, or you can say the stepwise procedure for the design of continuous one-way slab. So in this part I have covered the step 1 to step 6, and in this second part I have covered the step number 7 to step number 11. So let us move ahead. So these are the codal provisions or the codes required. First, you required IS 456 2000, and second you required SP16. So the question is like, the design a continuous one-way slab of clear span 3.2 meters, width of support 300 millimeters. This slab is continuous over 3 span. Use grade of concrete M25 and grade of steel Fe 415. Consider floor finish as 1 kilonewton per meter square and live load as 3 kilonewton per meter square. Here the figure shows the three span one-way continuous slab. So the given data is the data are provided as the clear span as 3.2 meters, width of support 300 mm, number of span 3, the grade of concrete M25 and grade of steel Fe415, floor finish is 1 kilonewton per meter square and live load is 3 kilonewton per meter square. So the first step is to calculate the effective depth. So to calculate effective depth, you have to do Lx upon D is equals to KT into its effective depth ratio. So the 1.3 comes from as there is a continuous slab, we have to multiply it with 1.3, so we have provided 1.3, and 26 comes from it is provided in the IS 456 2000 page number 37. It says that the vertical deflection limit may generally be assumed to be satisfied provided then the span to depth ratio are not greater than the values obtained at below. So basic value of span to effective depth ratio for span up to 10 meters. So it is usually used for span up to 10 meters. So as our span is 3.2 meter, so as the slab is continuous slab, so its value will be 26. So we have provided the value as 26. Now as the value of Lx is 3.2 meters, so I have provided 3200 mm, and the depth we have to calculate. So by making subjective to the small d, we have found the depth of the slab as 94. So we have to round off and increase the value. Do not decrease the value. So we have taken 95 mm. So the effective depth or the small d of the slab is 95 mm. So to calculate the capital D, we have to do is add small d plus clear cover plus diameter by 2. So I have taken here the diameter of reinforcement as 10 mm, and the clear cover for the slab is 20 mm. So by taking this, I have found that the small d is 95. So small d, the value of small d is 95 mm. Clear cover we have taken as 20 mm, and the diameter of bar 10 mm. So 10 mm divided by 2, so 5 mm. So we have the capital depth or the overall depth of the slab as 20 mm. So we have found in this the solution or the outcome of this step is the small d is 95 mm and the capital D is 210 mm. So the second step is to calculate the effective span. So as per the IS 456/2000, page number 35, clause number 22.2b. So it says that BS should be less than 1/12 into clear span. So let us read B point. Continuous beam or slab. In the case of continuous beam or slab, if the width of support is less than 1/12 of clear span, the effective span shall be as 22.2. A. If the support are wider than 1/12 of the clear span or 600 mm, whichever is less, the effective span shall be taken as under. It says that the BS should be less than 1/12 into clear span. If it satisfies, we have to move with the case A, and if does not satisfy, then we have to move with the case B. So let us read second point. For end span with one end free and another continuous, the effective span shall be equal to the clear span plus half the effective depth of the beam or slab, or the clear span plus half the width of the discontinuous support, whichever is less. So we have taken the width of the wall is given as 300 mm and the 1/12 into clear span. So the clear span is given as 3.2 meter. So it does not satisfy this criteria. So we will move with the case B. So case B says that the effective span should be calculated by as clear span plus D. So we have found out the effective span is 3.5 meter. If in case this criteria satisfies, then we have to calculate the effective span by using case A. That there is in case A there are two things. First point is center to center distance and second point is clear span plus D. We have to take the minimum of these two, so it will be the effective span, but in our case it is the case B. So we have calculated the effective span. So now let us read the second point. So the second point says that the effective span shall be if for end span with one end free and the other continuous, the effective span shall be equal to the clear span plus half the effective depth of the beam or slab, or the clear span plus half the width of the discontinuous support, whichever is less. And the third point says that in case of spans with the rollers or rockets bearings, the effective span shall always be the distance between the center of the bearing. So we have provided the effective span as 3.5 meter over here and 3.5 meter over here, as our case is the roller or the rocket bearings. So we'll have the effective span between effective span will be the effective span will remain as the clear span for the roller support. So let us move. The third step is maximum dead load and live load. So the dead load is already provided. The provided is 3 kilonewton per meter square. So we have to multiply with 1 meter to 1 meter to have the quantity or the estimation for the 1 meter square of that area. So we will multiply it with the 1 meter. So we will have this as 3 kilonewton per meter. So we have to find the load or the reinforcement for per meter of the length. So we'll multiply with 1 meter length. Similarly, the dead load will be calculated as 25 as the density of concrete into thickness of slab, which is capital T, overall depth, which is 120 mm. It is converted into meter into 1 meter. So we'll have the dead load as 3 kilonewton per meter, and the floor finish is already given 3 kilonewton per meter square into 1 meter. We'll have 1 kilonewton per meter. So the dead load plus live load will be 4 plus 3. 4 comes, the dead load will also include floor finish, so 3 plus 1 4, and the live load is 3 kilonewton. So after this we have to make as ultimate load. So for making ultimate load we have to multiply it with the factor of safety of 1.5 meter. So after multiplying we'll have the dead load as 6 meters and the live load as 4.5 meters. So here the diagram shows the spans and the loading condition. So the load is W dead load and W live load, 6 plus 4.5. So we have calculated these two things. So now we have to go to the IS 456 2000, page number 36, at that table number 12, bending moment coefficient. So we have to plot this slab with the 3 span and of loading 6 plus 4.5 kilonewton per meter as a dead load and live load. Now we have to write the values of alpha D and alpha L. So the coefficient of dead load and coefficient of live load. So here that IS 456 2000, page number 36, table number 12 shows the bending moment coefficient. So let us first start with the span moment. So for this span moment, near middle of the end, so near middle of the end, so it is, so here is the span. So for this span, here will be the sum of the values. So it shows that the near middle of the end span, and near to the end span is plus 1 by 12. So we'll have plus 1 by 12 over here. Similarly, near middle of the end span, so it will also make over here as 1 by 12. And the second, it shows that at middle of interior span, this is the middle of interior span. So interior span, as it is the external span, these are the external span, and 3.2 is the interior span. So the interior, for the interior span, the dead load coefficient will be 1 by 16. So we have provided the coefficient as 1 by 16. Now let us move to the support moments. For the support moments, at the support next to the end support, at the support next to the end support, this is the support next to the end support. So that at that we have to provide coefficient as 1 by minus 1 by 10. So we have provided coefficient as 1 by minus 1 by 10. At other supports, at other interior supports, for example, if we have the support over here, so at that support we will have the value as minus 1 by 12. So if the interior supports are provided, then the coefficient we will take as minus 1 by 12. But in our case there is no interior support, so that value will be neglected. So, and as this is the simply supported beam, so the bending moment at the support will be 0. So we will provide 0 0. Similarly, for the live load we will provide for the ends as 0 0. So let us move to the imposed load or the live load. First we will see the span moment. So near mid of the end span, which means we are talking about this. So the value is plus 1 by 10. So we will provide plus 1 by 10 and plus 1 by 10. Next, at the middle of the end span. So the middle of the end span, which means this, talking about this middle of the end span. So we'll have the value as plus 1 by 12. We will write plus 1 by 12 over here. Now moving on to the support moment. So at support next to the end support, this support next to the end support. So the support next to the end support is this one. So the value we will write as minus 1 by 9. So we will write as minus 1 by 9. Minus 1 by 9 and minus 1 by 9. So after doing this, we will calculate the moment. So for calculating the moment, we will have the equation as alpha d into WUD into LEX square plus alpha L into WUL into LEX square, which means coefficient of dead load into ultimated factorized dead load into length plus coefficient of live load into load or live load into the length and its whole square. So the we have the coefficient of alpha at the end support as here. We have 1 by 12. So 1 by 12 into the value of dead load is 6. So we will multiply by 6 into the span is 3 meters. So we will have the 3 meter plus coefficient of live load. So coefficient of live load is 1 by 10. So we'll write 1 by 10 into its load. Its loading condition is 4.5 meters and the span is 3.5 meters. So we'll write 3.5 meters. So we will have the moment at this point. At this point we will have the moment as 11.63 and similarly at this point. So next we will find the moment at this location. So mu, same equation, mu alpha d, mu is equals to alpha d WUD LEX square plus alpha L WUL LEX square. So coefficient for the coefficient for the dead load for the right hand side of the second. So right hand side of the second, which means this. So for this the coefficient is 1 by minus 1 by 12 and the dead load is 6 kilonewton per meter and the span is 3.5 meter. Similarly for the second thing or the live load coefficient, we have live load coefficient as minus 1 by 9. So minus 1 by 9 is minus 1 by 9 into its load 4.5 kilonewton per meter. So 4.5 kilometer per meter and the length is 3.5 meters. So 3.5 and its square. So we'll have the moment value as minus 13.47. So the so next we will find over here. So at this point, for this point we have the coefficient as minus 1 by 10 by into 6 into 3.2 its whole square. So it talks about this case, minus 1 by 9 into 4.5 into 3.2 its whole square. So we have found it as minus 11.26. So we have calculated like this. We have found, first we have find 11.63 At the ends, second we have found 13.47 and 11.26. By averaging these two values, we will have the value as minus 12.37, and similar over here minus 12.37. And similarly we have to find the moment at this point by using these two coefficients. So by using these two coefficients, we will have the moment at this point will be 7.68 kilonewton meter. So the fourth step is to check for depth. For check for depth, we use the equation as mu is equals to r bd square. Mu is equals to r bd square. So by using r bd square, so for mu the value of mu we will select as the maximum value which have been obtained from the calculation of the mu. So from this the maximum moment we have to consider. So from this the maximum moment is minus 12.37. So neglect the negative sign because it shows the negative and positive of bending moment. So we have taken the maximum bending moment as the 12.37 into 10 raised to 6. We have converted into Newton mm. So the value of r is 0.138 into 25 into b as 1000 into d square. So b as width as we have taken as 1 meter, so it will come as 100 mm. So the depth comes after making the subjective to d. We will have the depth as 39.88 meter, which is less than the 95 mm which we have calculated in the first step. So it is less and it is safe, so it is under reinforced section. Now we have to calculate mu upon bd square. So we have to calculate mu upon bd square for all these value. So first we will find for this thing, then the second we will find for this thing, and third we will find for this thing. So we will take mu upon bd square. So mu we have taken first value from here, so 11.63 into 10 raised to 6 upon b 1 meter, so 1000 mm into depth as 95 mm and its square. So we will have mu upon bd square as 1.28. Second, mu upon bd square, so the value of mu will take from that figure, so minus 12.37 into 10 raised to 6 divided by 1000 into 95 and its whole square. So third we will have the mu upon bd square. So the value of mu will be 7.6 into 10 raised to 6, which comes from here. So here we have provided 7.68, and we will have the value of mu upon bd square as the 0.84. So here we have found 3 mu upon bd squares. We have to put that mu upon bd square over here. So we have find mu upon bd square for this value is this. So we have written the value from here. For first point we have calculated mu upon bd square as 1.28, so I have written as 1.28, and similarly over here 1.28. For the second it comes from here minus 1.37 for the second, so minus 1.37 it comes from this value. Similar for this, and for this the third it comes from there. This value comes from 7.68, so it is 0.84 which comes from 7.68. After doing check for depth, we have to move for the area of steel in tension. So For calculating the area of steel in tension, we have this equation as percentage of steel is equals to 100 into area of steel upon B into D. So we don't have percentage of steel, we have width as 100 mm and depth as 95 mm. By making subjective to the area of steel, we can found the area of steel for all these moments. So the we need is percentage of steel. So we have the value of mu upon bd square. So by going to SP by using SP16 page number 49 table number 3, which shows the value of mu upon bd square, by seeing the value of FCK 25 Newton per mm square, it provides the value of percentage of steel. So in first case we have found the percentage of or the value of mu upon bd square as 0.28. So we have to see the value of 0.20 sorry the value as 1.28. So we have to observe the value as 1.28 in this column. So there is 1.25 and there is 1.30. So we have to take the higher value as to see the percentage of steel. So as the mu upon bd square, we have the value of mu upon bd square as 1.28. So I have taken as 1.30, and the grade of steel is Fe415. So going through this column and going through this column and row, so we will found the percentage of steel as 0.385. So for first point here we have find 0.385. So just we have to put the AST is equals to value of PT as 0.385 into B as 1000 into depth as 95 divided by 100. So area of steel in tension will have 365.75 mm square. For second step, we have calculated the mu upon bd square as 1.37. So we have to move on this table and we have to see 1.37. So here there is two value 1.35 and there is second value 1.40. So take the maximum value. So we have taken as 1.40 and the grade of steel is 415. So by seeing that row and column, we have found the value of percentage of steel as 0.417. So we have to put minus 0.417 into 1000 into 95 divided by 100. So you have found the area of steel in tension as minus 396.11 mm square. For lastly we have calculated mu upon bd square as 0.84. So we have to observe in this. So 0.84, which comes as 0.85. So see that row and column, and we have found the value of percentage of steel as 0.246. So we have to place the value of that as 2.246 into 1000 into 95 divided by 100, which provides the area of steel as 233.7 mm square. After that we have to write in this form. Initially we have found alpha D alpha L, so we have written in this form. Next we have founded the mu, so we have written in this form mu. So next we have founded mu upon bd square for all these part, so we have written in this form. Next we have calculated or we have found the percentage of steel as per using SP16 and table number 3. So we have to write the values of PT over here, and we have found the area of steel. So we have to write the area of steel required in this form. So we have calculated this quantities. So moving next, we will provide the reinforcement. So step 6, we will see the reinforcement. So first we will provide reinforcement at the center. Always provide reinforcement at the center. So we will firstly provide the reinforcement in this and in this point, which means it is the center, and then we will provide at this point, and lastly we will provide reinforcement is this and by using this area. So first, for the first, we will find, as we have the area, we will find the number. So number, for finding the number, there is a equation. Number is equals to capital AST divided by small ast. This capital AST is the AST which we have founded in this step number 5, area of steel in tension. So 365.75 mm square comes from here. Here it is. Here it shows 365.75 mm. As I told, we have to start from the center of the span. So we have found, or we have placed the value of capital AST as 365.75 mm divided by small ast. Small ast means area of that reinforcement. So we have assumed in the first step as the area of steel as, or sorry, the diameter of steel as 10 mm. So we will have the area as pi by 4 into 10 square. So we have found that the number of steel will be 4.66 numbers or 65 numbers. So now we will find the spacing. So spacing of that bar can be calculated as 1000 divided by number. This numbers we have found as for per meter. So per meter it will be 55 bars, we can say. So for spacing we will find the spacing as 1000 divided by number. So 1000 divided by 4.65. We have got the spacing as 214.7 mm. Do not increase the value of spacing. We can reduce the spacing, but we cannot increase the value of spacing. So here, to make it round, as a round figure, I have reduced and make the value of spacing as 210 mm. So as per IS, the maximum spacing for between two bars should be 300 mm, which satisfies. So we can place this bar. So we can say that we can provide 10 diameter bar 210 mm spacing center to center. So at middle, which means for this value 233.7. so number is equals to capital AST upon small ast. So capital AST area provide is 233.7 divided by small ast, which means area of reinforcement we have taken as 10 mm. So I have found the number of reinforcement per meter as 2.97. So I have calculated. So next we will calculate the spacing. So spacing can be calculated by 1000 divided by numbers. So 1000 divided by 2.97. So we have found the spacing as 336.70 mm. As per IS, the maximum spacing between two bars should be 300 mm. So we have to make it as 300 mm only. So we have make as 10 diameter 300 spacing center to center. Now for support next to the end support, we will see. So we will see for this point, for support next to the end support. So we will provide 10, 410, 240 and 8, 420. As here we have already provided at this support, at uh, at this support we have provided the steel as 10 of 210. So the coming on this at this support, the spacing, there will be alternative bends up. There will be alternative bent up of the bars having in the 3.5 meter of the span. So the center to center distance of the bar provided in 3.5 meters will be doubled at this support. So we have provided as 10 diameter, 420 center to center. Here and this second thing, there will be bar coming from this this support, or the this span of 3.2 meter, which is 10 of 300 mm center to center. But this has been reduced. I have reduced this as 8 of 210 center to center, because as per the IS code the maximum value should be 300 mm. So to reduce this spacing, we can also arrange the bars, diameter of bar. So I have changed this 10 of 300 mm to 8 of 210 mm. So at this support, the bar coming from 3.2 meter of span will have the alternative bent up, and at this support the spacing will be doubled. So the spacing is doubled and it has the diameter of 8 and spacing of 240. So we have calculated the area, and we have the total ASTS 306.6 mm square. Now we have to provide the extra top bar. Extra top bar will be provided over here when when one reinforcement comes from here, it will bend over here, and the second reinforcement will come from this point. These two will be overlapped, and over it the extra top bar will be provided, connecting the reinforcement coming from the 3.5 meter of the span and the second reinforcement coming from the 3.2 meter of the span. So the extra top bar is provided at this support, intermediate supports only. So here will be one of the extra top bar, and the second will be extra top bar provided over here. So we'll calculate the area of the extra top bar. So for extra top bar, we can see that from this one of the steel will come, and from this from 3.5 meter of the span the steel will come as 10 dia 240 center to center, and from this span of 3.2 meter will come as 8 of 240 center to center. So its total area is 306.6 meter or mm square. Now we have to deduct this area from the area which we have required. So the required area we have calculated as over here as 396.15 mm square. So we have to deduct this area 306.6 provided area from the required area at that support. So the required area at that support is here 396.15 is required, and we are providing as only 306.6, which means we are providing at support we are providing less reinforcement. So in additional to balance the quantity of reinforcement, we have to provide additional reinforcement, which is extra top bar. So by deducting this value, we will have the area of steel for the extra top bar as 89.5, and by this area we have found the diameter and the spacing as 8 diameter, 420 center to center spacing. So this is the reinforcement diameter and spacing. So at this support, or at this support to the left hand side, the bar coming from the 3.5 meter of span to the left hand side, or the last or the initial support, will be doubled, as there will be alternative bent up like this. So this spacing will be doubled. So the spacing will be 420. Similarly, at this support there will be spacing as 420. So thus part 2 for the design of continuous one-way slab is provided in the description box, and we will see the check for shear, deflection, development length, distribution bar, and figure for the continuous one-way slab in detail. The link is provided in description box. Let us see and thank you for watching this video.